Okay, here's a screencast on continuing in stoichiometry. Our objectives of the screencast is to be able to relate the mass of any component of a chemical reaction to the mass of any other component of that same reaction, and also to be able to relate the volume of a gaseous component to either the mass or the volume of any other component. One important thing to remember from a past unit is how to go from mass to moles, or mass to volume at STP. So for instance, if I have 4.00 grams of helium, remember that we want to relate grams convert to moles. How do we relate those grams and moles? Again, it's molar mass. For helium, from the periodic table, the mass is 4.0. Okay, so that would end up to be 1 mole of helium. And I neglected my sig figs, so it's 1.00 moles of helium. Okay. The other important relationship to remember is that there are 22.4 liters in 1 mole for any gas at STP. Standard temperature and pressure, that means 0 degrees Celsius, 1 atmosphere. Okay, so these are important things to take down. The steps for calculating the masses of reactants and products in chemical reactions. 1, you have to have a balanced equation for that reaction. 2, convert the masses of the reactants or products to moles. And this is really going to be converting the given, given information. If it's given in mass, we're going to have to convert to moles. Use the balanced equation to set up the appropriate mole ratios, meaning the mole ratio between what you're given and what you're looking to find. Okay. And then use that mole ratio to calculate the number of moles of the desired component of that reaction. And then you're going to convert back from moles back to mass. Okay. And here we can add, I was going to add or volume. All right, so if they say mass, we can also find volume. All right, this is stoichiometry. It's the process of using that balanced chemical equation to determine relative masses of reactants and products involved in a reaction. And this is really used every day in industry. If you want to make so many grams of your product, what do I have to start with? What raw materials do I have to put in that reactor? So the easiest thing is to go through an example. So we're going to look at the following unbalanced chemical equation, and we're going to calculate how many grams of chromium-3 oxide can be produced from 15 grams of solid chromium and excess oxygen gas. All right, so the first thing we have to do is balance the chemical equation. All right, so if I look at this, I have 3 oxygens on the product side, 2 on the reactant side. I'm going to, in my head, say, ooh, I know that that's going to have to be 6, so I would balance it that way. You may go about it another way. That's kind of the shortcut when you've been doing it for a while. All right, so 4 chromiums reacts with 3 oxygen molecules to produce 2 chromium-3 oxides. If you look at this problem, I'm given one number in the problem. I'm going to start with that number, 15.0 grams of chromium. In our steps, we have to convert that grams to moles so that we can then relate the chromium to the chromium-3 oxide using the moles in the balanced chemical equation. So grams chromium in 1 mole chromium using the molar mass from the periodic table. I have 52.00 grams. My next step is to relate moles of chromium to what I'm looking for. Well, I'm looking for moles of chromium-3 oxide. What's the relationship of moles of chromium to moles of chromium-3 oxide? I have to look at my balanced chemical reaction. For every 4 moles of chromium, I'm going to produce 2 moles of chromium oxide. But it asks me for the mass of chromium oxide. So, chromium 3 oxide, moles. How do I relate that to grams of chromium 3 oxide? Molar mass. Add 2 chromiums, 3 oxygens together. You should come up with a molar mass of 152.00. Grams of chromium cancel, moles of chromium cancel, moles of chromium 3 oxide cancel. I'm left with grams of chromium 3 oxide. If you do the math, 15 divided by 52.00 times 2 divided by 4 times 152 gives me 21.9 grams of chromium 3 oxide. Now, I can add another question to this, and it can say how many liters of oxygen are used at STP. Okay. So I'm going to add the question. How many liters of oxygen are consumed? Okay. I'm going to start with the 15.0 grams of chromium again. I have to use that molar mass to get to moles so that I can then use the mole ratio. But this time I want to relate moles of chromium to moles of O2. From the balanced chemical equation, 4 moles of chromium for every 3 moles of oxygen. In 1 mole of oxygen at STP, I have 22.4 liters. That will give me liters of oxygen. I don't have that math ready, so we're going to take 15 divided by 52 times 3 divided by 4 times 22.4. I get 4.85 liters of O2 will be consumed in this reaction. That is how to do mass to mass and throwing in volume. So the idea is to get to moles to get the mole ratio. Then you can go to liters. If it's a gas, you can go to mass if it's a gas or a solid or a pure liquid.